Okay, starting with the third advanced technique, so we'll be having the integration by parts. So this is the formula. So the integral of u dv is equal to uv minus the integral of v du. So in the left part, so this is the format of your integral equation. So that should be the format. And on the right side, this is the corresponding answer for this format. So as you can see, we have uv, then we have another integral which is minus v du. So we need to integrate again, but this integral, the minus v du, is, so it may be a simple, so integrate you may integrate directly, or you may have to proceed to another technique. So it will depend on the degree of difficulty of the given integral. But as much as experience tells me that I think you may integrate it directly, or you may have to use integration by parts again, or you may have to use another technique in the second integral. So where does the formula came from? So recalling our product rule, so product rule in derivatives, or the chain rule. So the derivative of um, so the derivative of uv is equal to u dv minus v du. So if you want to integrate the right side to go back to the original uv equation, so integrating both sides and isolating this part here, so we have the integral of u dv is equal to uv this one is plus, this product rule, minus v du. So this is the formula. Okay, so it came from the product rule. Now, what's the purpose of using the integration by parts? So if we go to the second description here, the bold part, so you may use, and so you have to use integration by parts if you have the products of two different functions. So what do you mean by this? So let's say we have an algebraic term, let's say x squared. Then we have a trigonometric term. So let's say sine 2 theta or 2x. So as you can see, the two terms are of different functions, right? So one is algebraic, one is trigonometric. So this is the time that you're going to use integration by parts. So it could also be exponential against trigonometric. So let's say e to the power of 2x, then you have sine x. So it could also be that product of the different functions. So also algebraic. Then let's say logarithmic. So that will be, let's say, x. Then this will be is ln x plus 1. So as long as you have two different functions, so you may use integration by parts in the process. So another one is logarithms. So we can use integration by parts if you have to integrate logarithms, because again, if you recall our topics before, so there's no integral for logarithms. So we may integrate logarithms now through the technique called integration by parts, as well as your inverse trigonometric functions. Okay, so for example, we have to integrate arc second, or here in logarithms, we have to integrate ln of x plus 1. So through integration by parts, we can now solve these special equations, special functions. So they are special because they don't have any formula for integrals. All right, so tips in this technique. So the process for integration by parts is we need to follow this format here. So I'm going to create a bold arrow. So we need to choose u and dv so that we can follow the format given above. So since we're going to choose dv and u, so the first tip is dx is always included in dv. So for example, the first statement is what the first statement is trying to tell us is, for example, you're going to have x e to the power of x. So let's say you let dv be something here in the equation. So let's say dv is equal to e to the power of x. So you must include dx. Okay, so your u parameter is x. So that's how you declare your terms. Okay, so for the second and the third one, so I think this one is a combination tip, a combined tip. So the second one is it must be possible to integrate dv directly, and it is best usually to choose the most complicated factor or term as your dv. So I think to sum the second and third statements, so the most complicated term, or factor is possible to integrate. So that's what you need to remember in your dv term. Okay, so the most complicated factor is possible to integrate, and don't forget to include dx. Okay, so how about tips for the u parameter? So of course, what's left in the equation is going to the u parameter. So I think what we can add here is your u parameter. So instead of possible to integrate, so your u parameter is possible to derive. Possible to derive, or easy to derive, or easy to derive. So it may be an easy term, it may be a difficult term, but as long as you can derive your u parameter, or it's easy to derive, so it's okay to have that term as your u parameter. But we must observe the dv all the time. So most complicated term for dv, and it should be possible to integrate, and then dx should always be included in dv. So for you to appreciate the terms that I have discussed, so let's go to some examples. So let's try to solve 8, so excluding number 6, because this one is an advanced technique. So I wasn't able to teach you this one because I think it's difficult, because you need to use reduction formula for the integral here. And I don't think this one will come out in the exam also. Okay, so let's try to solve the 8 other problems. So as you noticed, so these are different functions being multiplied against each other. So algebra against exponential, algebra against trigonometric. We have a logarithmic term, an inverse trigo function, trigonometric against logarithmic with a base of trigonometric, exponential against trigonometric, algebraic against exponential, exponential against trigonometric. So see the difference. So you'll be having different terms here. So let's proceed to number 1. So as what the tip has stated us, so I think you just need to follow what I'm going to do here. So since we're going to achieve the integral of u dv na format, so we have to declare first u. And then my suggestion for you is you write dv in this manner. So dv on the lower right. So there's a purpose why we need to write it in this manner. So later on we will try to see what it really looks like. So again, we need to look at dv first, this one. So it states that we must choose the most complicated term, and that term must be easily be integrated. So among the two, x times e to the power of 2x, so the most complicated term is e raised to 2x. Then again, don't forget the x. So looking at e to the power of 2x, so can we integrate e to the power of 2x? Yes, we can integrate e to the power of 2x because we have a formula for that one. So the other term, the x term, goes to the u parameter. So notice that there's nothing left to declare in the equation. So everything has been declared to uv and the u parameter. So next step is, since there's a portion there in the previous slide that we need to integrate dv, it's possible to integrate dv. So integrating dv, so we're going to have 1/2 e raised to the power of 2x. Okay, so integrating, and then we need to derive du. So du is equal to dx. So this one is derived. Okay. So why do we need to derive? Why do we need to integrate? Because in the formula, so let's write the formula. So the integral of u dv is equivalent to uv minus v du. So we need the v du here. Also for the u parameter here. So that's why we need to derive and we need to integrate your u and dv parameters. Okay, so let's go back to the red ink. So equals, so uv first, so x times 1/2 e raised to the power of 2x. That's your uv, minus the integral of v du. So 1/2 e raised to the power of 2x, then times du, that will be dx. So simplifying the equation so that we can see if we can still if we need to do some advanced techniques or some basic stuff only. So we have 1/2 times x e to the power of 2x, then minus, so take the constant outside the integral symbol, that will be 1/2 the integral of e raised to the power of 2x dx. So looking at the remaining integral, so this one is an easy integral. So the final answer is 1/2 x times e raised to 2x minus 1/2 times 1/2 e raised to 2x plus c. So this is the final answer. 1/2 x e raised to 2x minus 1/4 e raised to 2x plus c. So this is the final answer. Okay, so do you have questions for the first example? So most likely the procedure for the integration by parts will be repetitive because you'll be declaring u and dv in the terms first, then integrating dv, and then deriving u, and then following the format of the formula. So I think that's what you need to do always in integration by parts. And in my experience, so the easiest advanced technique for me is the integration by parts. So of course, as long as you know how to integrate and derive your dv and u parameters. All right, so do you have questions? So no question. Okay, so let's proceed to the next example. So this time is we have the product of an algebraic term and a trigonometric term. So starting off with your u again, so always again write it in this manner. So u and then dv here. Okay, so it's obvious that our complicated term is secant squared x, secant squared x dx. Then the other term is x. So can we integrate secant squared x? So yes, of course we can integrate that one because we have a formula for the integral of secant squared. So the integral for secant squared x is tangent x. Okay. Then the derivative is dx. So by formula, so let's try to, so again that's uv minus the integral of v du. So starting with uv first, so x times tangent of x minus the integral of v du. So that's tangent x dx. Okay, so looking at the integral of tangent x, so of course we have a formula for this one. So the final answer now is x tangent x. So this will be minus, and then minus ln of cosine x plus c. All right, so this becomes x tangent x plus ln of cosine x plus c. Okay, so if you're going to verify this one in Symbolab, so I think the answer in Symbolab is ln secant. So, or in other integral calculators, so your negative ln of x, negative ln cosine of x can be represented as ln secant because this one becomes ln cosine of x then raised to the power of -1 because That's the property of logarithms. The coefficient of the logarithmic function is the exponent of the base. So applying this one here, so this becomes ln secant x. So the other possible answer for this one is um, I'll add it here. So x tangent x minus, so instead of plus it becomes minus ln secant x plus c. So if you want that in that term, so you can also use this as your answer. So it depends on how you use the tangent x formula. So if you're going to use negative ln cosine x, or you're going to utilize the positive version, which is ln secant x. Okay, so questions or clarifications? Okay, so let's proceed. So this time as we go to the logarithmic aspect. So looking at your equation, so again, there's no formula for an integral for ln. But we do have an integral for this format, du over u, that gives us the ln answer. Diba? So, so we have this formula, but we don't have any integral for ln of u. We don't have this formula here. So since we don't have this formula, so we're going to use integration by parts. So u and then dv here. So again, if we're going to put ln here, ln x, since it's the complicated term, so notice that it's difficult to integrate. So because again, we don't have any formula for the integral of ln. So meaning we can't put ln x here, but we can put the ln x in the u parameter, because we can derive ln x. It's possible to derive ln x. So ln x is in the u parameter, your dv is just dx. Okay, so integrating first, so v is now the x parameter. So du, so again, the formula for ln u is du over u, so dx all over the x term. So notice that we can easily derive ln x. Okay, going back to the formula, so we now have uv minus the integral of v du. So ln of x times x minus the integral of x times dx all over x. So canceling out the x parameter. So ako lang yan para kita. So we have x ln x minus the integral of dx. So our answer is x ln x minus x plus c. Okay. So we have solved the logarithmic integral with an advanced technique. So questions? Okay, so wala. Okay, so let's proceed with the fourth example. So this time is we have your inverse trigonometric function. So again, starting off with your u and your dv term here. So if we put dv as your arctangent, if you let your arctangent be your dv, so again, it's impossible to integrate. So we put your arctangent square root of x here. And then your dv is your dx. So always try to check if everything in the equation has been replaced or can be declared as your u or your dv. So there's nothing left to declare. Okay, so starting with the integration of dv, so we have the x parameter, so the derivative of your arctangent. So again, if you recall your derivatives, so arctangent u over a, that will be, so the derivative of this one, du. Derivative of this one is du all over a squared plus u squared. Okay. So if you try to derive square root of x, so u is equal to square root of x. So derivative of the square root of x is 1/2 x raised to the power of negative 1/2. And of course, looking at the arctangent square root of x, so a is equal to 1. So what will happen is we're going to have 1/2 x raised to the power of negative 1/2 all over a squared, that is 1, because 1 squared is still 1. And then your u squared, so this one here. So u squared is now the x parameter. So plus x. Okay, so simplifying is we're going to have, so this one is dx. So we're going to have dx all over 2 square root of x times 1 plus x. So this one is your du parameter. Okay, so formula uv minus the integral of v du. So again, I hope you got the derivative part. So I think you can get the derivative part because you have reached calculus 2, diba? So you know how to derive your equations. So that will be arctangent square root of x times x minus the integral of v du. So that will be x times dx all over 2 square root of x times 1 plus x. Okay, so we're going to have x arctangent square root of x. Then we have the integral of x dx all over 2 square root of x 1 plus x Or if you don't want to deal with the two in the bottom or in the integral below, so we can write this one as 1/2. So taking the constant outside, so that will be x dx all over square root of x 1 plus x. So how do we deal with the integral with the remaining integral? So the remaining integral has a, a radical expression in the denominator. So again, if we recall the discussion in the previous slide, so it states that the remaining integral may be integrated easily, or you may have to use another technique, or you may have to use an advanced technique to integrate your remaining integral. So as you can see here, we have a square root of x here. So as you recall, so since we discussed your algebraic substitution, so we can utilize that particular advanced technique. So let's try to use another color so that we can see how we're going to do with the integral. Okay, so I think I'm going to erase this one first so that we can have enough space. Okay, so let's try to isolate first the integral of x dx all over square root of x 1 plus x. So since we're going to use algebraic substitution, so we're going to let this as your z. So again, if you try to recall your algebraic topic, algebraic substitution topic, so we let the radical function be z. So that will be square root of x. So next step is to eliminate the radical expression by getting the square. So this becomes a z squared is equal to x. And the next step is we derive. So we have 2z dz is equal to dx. So your dx is this term here. Your x parameters is z squared. Square root of x is your z parameter. So we can now replace this one as the integral of x first, so that will be z squared, and then times 2z dz divided by, so square root of x, that will be z, then 1 plus z squared. So cancelling out z and z, so we have the integral of 2z squared dz all over 1 plus z squared. Okay, so we can also factor out 2. So we're going to have z squared dz all over 1 plus z squared. So notice that we have the same degree in the numerator and in the denominator. So we can use long division here. So let's try to put the long division in this corner lang here on the upper right. So this will be 1 plus z squared divided by z squared. So we have 1, then that will be z squared plus 1, then minus, then we have negative 1. So the answer for this one is 1 minus 1 over 1 plus z squared. Okay. So next step is we're going to have this integral now. So this becomes the integral of, so 2 integral of 1 minus 1 all over 1 plus z squared. Okay. So getting the integral, this becomes 2z minus, so 2. Then looking at this format, the integral of 1 over 1 plus z squared, so that's arctangent of z. Okay, so this one here will goes here. That's the answer of this integral. So we still need to bring back the value of z. So I forgot to bring back the value of z. So this becomes 2 square root of x minus 2 arctangent square root of x. So instead of the previous line, so this one goes here. Okay, so going back to the red ink, so we have x arctangent x minus 1/2. Okay, minus 1/2, this one, minus 1/2 times the answer of this one. Okay, so times 2 square root of x minus 2 arctangent. So it won't fit. So let's try to adjust first. So 2 arctangent of square root of x. So we have plus c. So don't forget plus c. So expanding, so by eliminating 2, because 1/2 times 2, then 1/2 times 2. So the final answer, so let's try to arrange it. So arctangent x, then using this term here, so we have plus, because minus, then minus. So we now have plus. So plus arctangent, so this one is square root of x minus square root of x plus c. So this is the final answer. So notice that in this particular example, so we have gone through many techniques in this equation. So using integration by parts, then we have also used your algebraic substitution. Okay, so questions or clarifications? Okay, so there's no question, so let's proceed. So this time is we have the integral of cosine x times ln of sine x dx. So starting with u first here, and then dv on the other side. So again, it's impossible to integrate ln of x. So we'll just have to put your ln sine x here. So ln sine x. Then the other one is cosine x dx. So looking at your dv, so it's possible to integrate cosine x. So this becomes sine x. Then your derivative for this one. So again, the derivative of an ln function is du all over u. So derivative of sine x, that becomes cosine x dx in the numerator all over sine x du all over u. Okay, so my tip here is don't try to replace this one with cotangent first, because we might be eliminating some terms. So to avoid reverting the cotangent back to its simple components, so just try to make this one as is as for now. So if it won't be cancelled later on upon applying the formula, so that's the time that you can convert it into cotangent. So uv minus the integral of v du. So that will be ln times sine ln of sine x, then times sine x. So I use bracket because since the base of the ln function is in parenthesis form. So minus v du, that will be the integral of sine x. So du is cosine x all over sine x times dx. So this is what I meant earlier, that so if we have this as cotangent x, and then we have this one as sine x times cotangent x, so you still need to revert it back again into its simple components because we need to eliminate sine x. Okay, so we now have sine x ln of sine x minus the integral of cosine x dx. So looking at the integral, so that one is easy to integrate. So the final answer is sine x times ln x, ln sine x I mean, minus sine x plus c. So this is the final answer. Okay, so no questions? Okay, so let's proceed with, so this one is skipped because this one is another topic, an advanced topic. So let's try to solve number 7. So u and then dv. Okay, so in this problem, so since the two terms are difficult to deal with, I mean the two terms are complicated terms. So I think for me, so I want my cosine going to dv. Okay, so why is that? Because if I put cosine x in the u parameters, so I'll be getting a negative du, and I don't want to be dealing with any negative signs, because usually what makes our equation wrong is we forget how to apply the negative signs in our equations. So that's just my my tip. So avoid dealing with negative symbols. Then the other term is e to the power of x going to the u variable. So of course, if trip ninyo mag-deal with negative sign, so if you want to deal with negative symbols, so you may have your um, cosine x into the u parameter so that you can get a derivative of negative sine x. So just don't forget to multiply the negative symbol. So this one is sine x. And then this one is du is equal to e to the power of x dx. Okay, so by formula, the uv minus v du. So we now have e to the power of x sine x, okay, minus the integral of v du. So that will be sine x e raised to the power of x dx. So notice that in the remaining integral, so it looks like the same as the original equation, but we're going to have a sine function. So we're going to use again integration by parts. So we're going to use it twice. So for me to be consistent with my declaration, so I'll still use the same values. So dv here is now sine x and dx. So dv here, so this becomes negative cosine now. So for me, it's okay to have negative cosine as my v so that I can have a positive value later. Then my du here is e to the power of x dx. Okay. So again, applying the formula for the second time. So we're going to have e to the power of x sine x minus the integral of uv. So that's negative e to the power of x cosine x. So minus the integral of negative cosine x e raised to x dx. Okay, so expanding. So we have e raised to x sine x. So minus minus, that will be plus e to the power of x cosine x. Then minus minus. Then we have a minus sign here. So we're going to have minus the integral of e to the power of x cosine x dx. So as you notice in the remaining integral, it's the same as the given equation above. So if we're going to use your integration by parts again, so you'll have an infinite integration by parts process, diba? So it won't end because you'll be going back again to your integral of e to the power of x cosine x. So how do we do this? So again, if we try to recall basic mathematics, let's say black color. So for example, we're going to expand here this term. So this one becomes x squared plus x, di ba? This is how we write the equation. So the left side is the equation, the right side is the solution. So let's say we try to create it longer lang siguro for you to appreciate what I'm trying to talk about. Okay, so for example, in this equation, so let's say we need to multiply the binomial first. So this becomes x times x squared plus x plus 2x plus 2. And then the next step is x and then x squared plus 3x plus 2. And then we need to distribute the x, so that's x cubed times plus 3x squared plus 2x. So in basic mathematics, so the correct way is for us to repeatedly write the original equation on the left side. Diba? Murag muna siya ang process always, the correct process. So we need to write it always in that manner. Then final answer is this one, diba? Because it's like an identity. So this term here is equivalent on the term on the right side. So why am I talking about this? Because of course we can do the same for this process. So we can write it on the left side here. So e to the power of x cosine x dx. And let's say we're going to write it here, e to the power of x cosine x dx here. So of course in our tradition, so we don't want to keep repeating on writing the original equation because it takes too much time, diba? So that's why we are just using the equal sign. But in actual practice, or let's say when you go to BS Mathematics, so this is the correct process for answering equations. Okay, so the purpose of having this one on the left side, or I mean the basic concept, is that upon looking at the remaining equation, since it goes back to the original equation, so we can group them together on the left side. But we can transpose it, we can move it, or we can isolate that particular term on the left side. So this becomes, so let me write it in black again so that you can appreciate the process. So this becomes the integral of e raised to the power of x cosine x dx. So transposing negative integral of x e to the power of x cosine x dx. So this becomes plus the integral of e to the power of x cosine x dx is equal to e to the power of x sine x plus e raised to the power of x cosine x. Diba? And then combining the two terms is we now have 2, the integral of e raised to the power of x cosine x dx is equal to e x sine x plus e raised to x cosine x, and then dividing everything by 2 because we have 2 as the coefficient of the integral sign. So the final answer is, of course, this one, e to the power of x sine x plus e to the power of x cosine x all over 2. So the integral of e to raise to x cosine x dx is equal to this answer, plus c. So that's how you do it when the integral equation is going back to the original equation. So you just have to group them together on the left side. So take note that your operation must be negative so that when you try to transpose it on the left side, so it becomes a positive value. Because if you have a positive sign here and then you'll be transposing it on the left side, so that becomes 0 because this one is negative na, diba? So try to remember that the remaining term or the equation that went back with the original equation is a negative sign. Okay, so did you get the process? Or do you have question regarding this example? Okay, so no question. So let's proceed. So sige lang, your number 7 will be discussed again in the last example, but with a different value na. Okay, so starting off with your U and your V again. So as you can see, it's very repetitive comparing with the other two advanced techniques, which are your trig sub and your algebraic sub. So it requires more analysis because you need to know what particular radical expression you're going to eliminate. Okay, so this one is, so for me, my difficult term is e to the power of 2x dx. So maybe for some of you, your difficult term will be x squared, so it depends on what you want as your dv. But for me, it's this one. So v now is equal to 1/2 e raised to 2x. So again, if you're wondering why it's 1/2, so since we have a coefficient in the numerator, I mean in the exponent, so the answer is 1 over a e to the power of au plus c. So this one is the same as the integral of, the same concept as the integral of sine au. So this one gives us 1 over a cosine au plus c. So those are the same concept. Okay, so next is your du here. This one is 2x dx. Okay, so starting off with the first one, so we're going to have x squared times 1/2 e raised to 2x, that would be our uv, minus the integral of v du. So that's 1/2 e raised to 2x times 2x dx. So canceling out the 2 here, then simplifying the equation. So we have 1/2 x squared e raised to 2x minus the integral of e raised to 2x. So we have an x value. So x times e raised to 2x dx. So as you notice, so still algebra against exponential. So we're going to use again integration by parts. So u now here is x, and then dv is e to the power of 2x dx still. So v is equal to 1 half e raised to 2x. And then your du is equal to dx. Okay, so we now have 1 half x squared e raised to 2x, and then minus, so the answer of the integral of the integration by parts, that's uv. So x times 1 half e raised to the power of 2x minus the integral of v du. So 1 half e raised to 2x dx. So expanding, so we now have 1 half x squared e raised to the power of 2x minus 1 half x raised to the power of 2x. So minus minus, so this becomes plus the integral of 1 half. So let's take 1 half outside. So 1 half integral of e raised to 2x dx. So now it's now simple to integrate. So the final answer is 1 half x squared e raised to the power of 2x minus 1 half x e raised to the power of 2x plus, so the integral for this one is 1 half e to the power of 2x times 1 half, so that will be 1/4 e raised to the power of 2x plus c. So this is the final answer. Okay, so there's a shortcut for this one, but it only applies with an algebraic term raised to any exponent. So let's try to this one. So shortcut. So the shortcut for this one, so it is only applicable with one term being algebraic. So it should be linear. I mean, it should be x raised to any power. So as long as n is not equal to one side, so it should be higher. So 2, 3, so on and so forth. Or x plus a raised to the power of n. So it could be x plus 1 raised to the power of something. Okay, and then the other term is any other function. Okay, so what we normally do is we create a table in this manner. So one is u, and then the other is v, dv. Okay, so on the left side, you have to derive everything as what we have done here. So the u parameters are being derived, and then the dv parameters are being integrated. So in the shortcut, so always place your algebraic term in the u parameter and the other functions as your dv. So in the example earlier, so the algebraic term there is x squared, and then the other function is e raised to the power of 2x. So what you need to do is we need to derive the left side. So this becomes 2x. Then derive again, you have 2. Then derive again, you have 0. So you stop here because derivative of 0 is wala na, diba? Still 0. So on the right side, you have to integrate. So let me write it here. So derive and then integrate on the right side. So you have 1/2 e raised to the power of 2x. Then you integrate this one again. You have 1/4 e raised to the power of 2x. And then you integrate this one again. You have 1/8 e raised to the power of 2x. So this is the process, diba? Okay. So next step is for us to multiply diagonally downwards. So this one in this manner. And then the operation for the multiplication of the terms are reversed. I mean plus minus. So plus first and then minus on the next term, then plus on the next term, then minus on the next term, so on and so forth. So if you're trying to look at the answer, so going to the first term here, so that will be 1/2 x squared e raised to the power of 2x. Then on the second term, 2 times 1/4, that will be minus 1/2 x raised to the power of 2x. Then on the last term is we have 2 times 1/8, that will be 1/4 e raised to the power of 2x plus c. So notice that the answer is the same as what we solved earlier. But of course, it only applies in these conditions. Kanisya. Shortcut. So it's very helpful to use the shortcut. So let's say you're going to have x to the power of 7, diba? Now, then you have cosine x dx. So if you're going to use the integration by parts manually, so you're going to use it 7 times to get the final answer, rather than creating the table and then getting the answer in such a short time. Okay, so questions? Okay, so no questions. So let's proceed with the final example so that we can discuss the midterm exam. So u here and then dv here. So for me, it's easy to derive sine 3x because what I have to deal with later is just the fraction coming from the exponential function. So e raised to 2x. So again, it will depend on you. If you want your dv be sine 3x, it could also be. But this is my way of solving the integration by parts. So of course you can verify if you let dv be equal to sine 3x and then your u be equal to e to the power of 2x, and we have the same answer baron or dili. I'm sorry, so e to the power, so sine 3x there, sorry. So this will be sine 3x. Okay, so getting the derivative and the integral of dv. So v is 1/2 e raised to 2x. And then your du function is, so this one is 3 cosine 3x dx. So where did the 3 came from? So of course, from formula. So if you have sine AU. So this is cosine AU times A, di ba? Wala siya ang formula. Okay, so for those of you who have forgotten why there's 3 in the derivative of sine 3x. Okay, so UV, so let's try to arrange it immediately. So 1/2, then e raised to the power of 2x sine 3x minus a v du. So that's 1/2 e raised to the power of 2x, then times 3 cosine 3x dx. So simplifying it even further, so we have 1/2 e to the power of 2x sine 3x. So 1/2 times 3. So taking out the constant immediately, so that will be 3/2 integral of e to the power of 2x cosine 3x dx. So notice again that it's still exponential against trigonometric. So again, repetitive process. So u is equal to cosine 3x, and then dv is equal to e to the power of 2x dx. So du is equal to negative sine, so negative 3, I mean, that's negative 3 sine x dx. So negative 3 sine 3x dx. And then v parameter is again 1/2 e raised to 2x. So this one is 1/2 e raised to 2x sine 3x. So minus 3/2, and then use the bracket because we have to utilize the formula uv. So that's 1/2 e raised to 2x cosine 3x minus the integral of v du. 1/2 e to the power of 2x times negative 3 sine 3x dx. So expanding, so 1/2 e raised to 2x sine 3x. So 3/2 minus 1/2, that will be negative 3/4. Okay, negative 3/4 e raised to the power of 2x cosine 3x. So negative 3/2 times the negative sign, and then 1/2, then times negative 3 pa dyan, di ba? So negative, negative, and then negative. So this one is still negative. Okay, so 3/2 times 1/2 times 3, that will be 9 all over 4. Then integral of e raised to the power of 2x sine 3x dx. Okay, so as you notice, the integral here is now the same as the integral above. So again, what we do here is, if we try to go very basic, so on the left side, there's an imaginary, na siya, always to be written unta, di ba? Always to be written the original equation. So we have to transpose this one to the left side. So having that one is we're going to have e raised to the power of 2x sine 3x dx. So transposing negative 9 over 4 to the right side, to the left side, So instead of minus, this becomes plus 9 over 4, the integral of e raised to the power of 2x sine 3x dx. So equal to 1 half e raised to the power of 2x sine 3x minus 3/4 e raised to the power of 2x cosine 3x. So this one is 1 plus 9 over 4. So that will be 13 all over 4. So 13 all over 4. The integral of e raised to 2x sine 3x dx is equivalent to 1 half e raised to the power of 2x sine 3x minus 3/4 e raised to the power of 2x cosine 3x. So divide everything or multiply everything by 4 over 13. So the answer is e to the power of 2x sine 3x dx is equal to, so 4 over 13 times 1 half. So that will be 2 all over 13 e to the power of 2x sine 3x. Then 4 over 13 times negative 3/4. That will be negative 3 all over 13 e to the power of 2x cosine 3x plus c. So this is the answer of your integral. Okay. So questions, clarifications, or violent reactions? 9/4 is this one here, so I'm going to circle it. So negative 3/2 times 1 half and times negative 3. Okay. So any more questions? So I think there's no more question.